All right, in this video, I'll be explaining USICO 2016 January contest goal with problem 1 Angry Cows. I'll be explaining the problem and then I'll also be live solving the implementation. So that might have some bugs, but the logic should be right. So if you came here for the logic, then it's good. I really like this problem, and um, it also didn't have a tutorial online. So the combination of those two kind of yells for me to upload a video. So basically, this is like the other problem. It's the same kind of theme. It's just different. What I mean by other problems, I mean the silver and bronze version. Those problems are really easy. This one's harder, but obviously because it's gold. But still, yeah. So basically, the goal is to start a single. The goal is to use a single call to start a chain reaction that detonates all the tables. So this time, you basically have the same type of setup you did last time, but you can choose any such position um, from x1 to xn. I don't know why you would choose a position outside that. That's really suboptimal. I mean, not even suboptimal. That's terrible. Terrible. That's not even optimal. But like, yeah, why would you choose that? Anyways, who cares? You can choose anything, right? Any position. It can literally be like 1.333, but why would you choose that? And if a cow is launched with the power of R landing at position X, this will cause a blast radius of R, engulfing all the halos with the range X minus R, X plus R. These halos that explode themselves simultaneously with the blast radius of R minus 1, and then if you explode, it's R minus 2, so on. Please determine the minimum amount of power R with which a single cow can be launched so that if it lands at an appropriate location, it'll cause subsequent detonation of every single halo in the scene. So I actually think, yeah, you can read the test case. We're not going to read the test case. I assume like you've done the minimum at least, and you've read through the problem before, and you've understood the test case. But anyways, we're just gonna get to kind of the derivative. I'm not just gonna tell you the solution. I'm gonna try to emulate like a solving path, kind of just with exploration, or just try to give you try to highlight the motivation of the solution. So like whenever you see like print out the minimum amount of power R and you have a simulation type problem, it's good to consider binary search. The binary search won't necessarily work, but a solution path, right? A uh, solution path to a problem that is like uh, print print out the minimum minimum let's say blank on a simulation function is to use like binary search, right? So and if you want to use binary search, right? If we want to use binary search, we have to look uh, for uh, we have to look for monotonic properties. That just means like search it up. I don't really want to explain it. It's a pretty self-explanatory. We have to search. We have to look for monotonic properties. Yeah, you have to look for monotonic properties in order to use binary search. So we're gonna try the solution path and just see, because it's a simulation type problem, and we're trying to print out the minimum x, and we'll just see if binary search is a good solution path. So basically, how the way this works is that we're gonna say, if we knew the radius beforehand, how could we like? So we're gonna try binary search means that we're gonna try a very we're gonna start with a very huge consideration of answers from like one, or you can even do zero. Really does not matter, from like 0 to 10 to the 12. So all the way to 10 to the 12. We're gonna start with a huge consideration space, and this will be the radius. So R will be in this set, right? R belongs to this set. And basically, if we knew the radius beforehand, how could we tell if that radius could work, right? How would we know if the radius would work? What would be the most optimal case of that radius? So essentially, we're saying if we knew like the radius, I'm gonna say this again because it's really important. If we knew the radius, how could we optimize the problem? Because for there's always a one-to-one correspondence between. There's actually two optimal cases per radius, and you'll see why, of the most optimal case for a radius, right? So like for the number line, let's say you have a number line that represents the problem, right? This is, I'll use blue, why not? This is left and this is right, right? So that's your first column, your last column. So we're trying to say, okay, we're trying to essentially find the start position for this fixed radius such that we have the most optimal case, right? The most optimal case is defined by exploding as many Hebels as possible, right? And then the idea is that my first thought was, hey, well, the most optimal case would always be the median, right? Might as well start an explosion in the middle because, like, the median on average is always like closer to everything. Central tendency and nonsense. I don't know. I don't know too much about stats, but like, yeah. So I was like, let's just do that, right? And this is wrong. I'm going to tell you why this is wrong. You might have not thought about this, but I think you kind of, it actually kind of helps to think about the median and then think about why that's wrong, because thinking about why it's wrong will actually lead you to the solution, right? So if I say this is the median, let's say the median explodes every cow on the left, right? So it detonates every cow on the left, right? And then the idea is that if it detonates every cow on the right, then couldn't we argue that we might as well try a position to the right of what we just tried? So we tried the middle, right? So we just try the middle. So we just try the middle for the radius for where we should like start the collision or the chain reaction. Then we could argue that might as well see if I push it like this. Let's see if everything explodes on the left and on the right, because obviously we know that it will explode on the we obviously know that it's going to explode on the right because we just pushed it closer to the right. But we're going to see, does it basically explode everything on the left, right? Essentially. And this is symmetric. You could also ask, could we go the other way? So could I construct the same type of philosophy with the other with another with by pushing the radius closer to one to the left side, right? So if this was the case, right, we had the case like this, then it also suffices to say, if this is the exploding everything, and then this is R, it also suffices, and then like it also suffices to push the start of the collision closer to the left. You would yield the same result and just keep trying, right? And you basically you do this through binary search. You binary search, like if you want to take the left case, which it literally does not matter. So this is like the left case because, or is it? Because we're trying. Hold up. Because we're trying to find. Yeah, this is the left case. I don't really know. Yeah, this is the left case, right? Because it's just nomenclature, right? So the left case is where we're just trying to find the position such. We're trying to find for a given radius, right? We're trying to find the left position that explodes the most right position, right? We're trying to push the uh uh what should I say, the radius, the start of the collision, further to the right as possible, such that it explodes every left cow. Because we know that as when it pushes further to the right as possible, then we increase the chance of exploding every cow on the right of the start of the collision. And that's where the monotonic property, and the same thing can be applied to the right case. I won't explain the right case, but that's kind of the monotonic property. So the idea of this is that uh, for a fixed radius, it's a it suffices to push the start of the collision to one end of the number line as far as you can, such that you can explode every cow on that end. Uh, since the cases are symmetric, like it's literally just symmetric, uh, then it doesn't matter what case you choose. Um, I will be choosing the left case. Why not? So uh, let's say we just choose left case. Again, it doesn't matter. But the idea is that if you can push the start of the collision as close as you can uh, to an end, then you're optimizing the best case for that radius because you're increasing the chance that the other end is exploded because you already know that what you're searching for, you already know that the other end is exploded. So to increase the chance that the other end will explode, then you just push it closer to that end. And the way that we will do this through binary search is we'll start in the middle. So uh let me just yeah, we'll start in the middle. I don't want to cover that. So actually, whatever. So we'll start in the middle, right? So left and right, um, and we'll try to basically say we'll see does this work? Does it explode every cow on the left? Does it explode every? And if it explodes every cow on the left, then it suffices to move the left here and the mid here, um, because then we'll just see. Um, it suffices to make the mid position not yeah, it suffices to make the middle position like over here, like move the left over there and then make the mid position here, and then just see does it explode every cow on the left again. And if it doesn't, then we make r this, and then L still this, and then we do a mid, and then we just see does it explode every cow on the left. So the idea is that like you start from the middle, right? And you see does it explode every, because we're taking the left case, we're trying to binary search the farthest position right in the left case. So we first just say check, okay, on average the positions at the middle, right? So if when cases get larger, so we test the middle and we see, okay, can you explode every cow on the left? If you can explode every cow on the left, then just basically binary search, move the pointer to mid, and then take the averages of those distances, and you'll have a new position through that binary search type property. And then you just try it, and if that doesn't work, then you move the right pointer at that place, and then you take the mid over there. So the idea is that you're the distance you're using like two pointers and mid distances to like help you binary search the idea. So once we binary search the idea, then all we have to do, so basically what I'm going to say, just to put this in simpler form, once we binary search the most optimal case for a radius r, we can then binary search the answer. Because if I know that, like, this is obviously monotonic, because if I know that radius, because because basically when you binary search the most optimal case for a radius r such that it works, right, and we define that as uh, pushing it closer to one end and then checking that both sides are pushing it closer to one end as much as possible and then checking if both sides work, right? We define that as the most optimal case. Well, if you just told me that you just found a case that's optimal, then you know that r plus 1 will work. You know that r plus 2 will work. You know r plus 3 will work, and so on. That's a monotonic property. So you can truncate that part of the consideration space, and vice versa. If r doesn't work, then there's no way that r plus 1 or r plus 2 and r plus 3 will work, because you tried as much as you can to optimize that case for r. And so if you didn't optimize it, there's no way r plus 1, r plus 2, and r plus 3 have any chance whatsoever. So that's the type of monotonic property that we can use. So that's basically the solution, right? And to simulate like the idea of pushing it, or for checking if every cow on the left is exploded, we'll just use sets, and you'll see this implementation. But this is really just the logic. I just want you guys to understand the logic of this problem. But Yeah, right. Let's actually implement it. All the implementation quirks, I guess, will be explained. This is really not a quirky problem, but yeah, let's just implement the problem. I think it was a pretty cool problem, so we'll implement it now. So, and I'll also explain more as I implement, I guess. So if you didn't understand it now, hopefully, you understand it more. So public static. What? I don't know why I'm not using it. I know there's a template, but like, uh, I deleted everything because it's a live solve. I literally start from scratch, my guys. Yeah, it literally does not matter, but whatever. Okay. Yeah, I really like this problem. So I guess while we're doing input stuff, oh yeah, first I should input this so I don't get like 1,000 red underlines. But this problem is really nice. You just basically notice like, yeah, and I really like the symmetry in the problem. Like you can pick either side and it's going to work because you're optimizing it every single time. Um, oops, hold up. Okay. So this is like obviously a useless part of the solution. Oh, also, I should probably explain something real quick. This is just like a uh percent of okay. This is just like a quirk, I guess there is a quirk, but basically when we're binary searching the radius, it's always nice to keep it as because like basically in order for an explosion to work between two hables, so hable one and hable two, we always have like h2, let h2 minus h1 be the distance, let this be d, then in order for this to work, then all we need is a radius of d over 2 um for this to work, right? Like it literally just needs boom and boom for a collision to happen. So like what we do in this case, we always want this to be even. We just multiply everything by two. So we multiply all the positions by two, and yeah. So I should probably explain that. We multiply just for convenience. You don't have to do this, but it just makes it more convenient because you don't want to have to consider like because then you could just divide by two in the end. You because the reason for this is because it's always possible to reach two hables by just doing a like uh like you could, for example, here and here, like if this is like how like the radius could literally be like if the distance in order to, how do I say it, in order to explode both of these hables, right, then what you need is a radius of you need a radius of let's say this was distance 3, then you need a radius of 1.5 to explode both of these hables. But it's really annoying to have to consider like doing that. So because it is annoying, we just multiply everything by 2 and then we'll just simulate it like it, and I'm just like, yeah, basically because the binary searching the radius given radius, because yeah, it's a little bit annoying. If that hopefully that makes sense. It might not make sense, but um, yeah, that's just one thing we can do to make our lives easier. So that's really not that part of the solution is really not that important. Like it really. So if you don't understand what I just said, don't worry. It doesn't really matter. That part of the solution is not that important. It's just for convenience. So the logic is the most important. That's obvious. So we have static and n. I'm gonna keep this all longs because this is a gold problem, and I assume they expect you to do this as a. Oh, yeah, we should probably talk about the time complexity. Time complexity of this code's like n log n, essentially just binary search. So yeah, and then like yeah, it's n log n. It's logarithmic, and you know to 50k, it's gonna work. I'm not gonna do like an in-depth analysis on the time complexity. My computer is like lagging, kind of. Okay, so we take an n. I'm gonna have to think about how. I had an idea to implement this. So we need the cows, right? Or hay bells, whatever. Did I call them cows? Whatever. I don't really care. So we use hay. We're also, or do we actually need a hay? Do we actually need an array? I think what I was gonna do is actually keep everything in a set. Yeah, I was going to use sets because sets have some nice properties. Like for the simulation of checking if every cow is exploded on on a particular end from a position. For that case, there's some really nice properties for sets. So I think using a set would actually be better. So yeah, using a set would be better. And yeah. So I'm actually gonna use a set, tree set, and everything's distinct. So yeah, tree set's really nice prop. Uh, yeah, see my computer's lagging. It's taking and I'm typing. It's lagging. But yeah, this is just because it's really convenient. You'll see why using a set is nice. Actually, yeah. So because we're multiplying everything by two, we should probably keep this as a long. Oh my god, it's really annoying. Oh dude, this is actually really lagging, bro. Stop lagging, computer. Um, actually, wait. Hold up. Anything?